As Mano introduced, it's about a program of work we call Smart Sensing and Imaging Systems, and it is about building a digital twin of an apple production system. I have to get the slide to move now. Here we go. I'll just shift the, that'll help me quite a bit. Good, sorry all. So there we go. This is the vision of our digital horticultural systems program of work, which is quite a large program of work, as you'll see. It's to build and validate a multi-scale digital twin platform that allow us to holistically simulate, interrogate, design, and ultimately prescribe and control the structure and performance of a perennial horticultural food system. And that's right across the value chain. Probably a key point to make here is that here at Plant and Food, we're building this for our science purposes at the first instance. We want to use this as a capture tool for our knowledge and to find the holes in our knowledge of these systems. Our initial exemplar is the plain accordion. It's a 2D growing system developed here at Plant and Food. Quite often colloquially gets known as FOPS. Royal Gala on an M9 rootstock is the initial plant material. So this program aims to be the real world sensing arm of that digital twin. It's one of 7 currently funded programs. You can see the program diagram to the right there, where the program in brown at the bottom left of that, and there's 3 modeling programs that can be seen in the center top. A little bit of an idea about the size and scale of that there. The modeling approach is multi-scale, so the plant models are done using functional structural plant modeling. So we need to sense essentially plant organs to feed that information. And there is also ecosystem scale models there as well. So quite a broad gambit of sensing required. So some of those basic modes are 3D architecture and plant organ metrics. Some microclimate sensing, both like quality and quantity. Proximal fruit quality. And we'll also be looking at in-field molecular and volatile sensing. And this is also providing capability development within the interdisciplinary teams. So there are engineers, data scientists, and a range of biologists all learning increasingly to work together towards these ends. And that's just in our sensing program. It's the wider program has obviously broad skills too. It's broken into 4 research aims. The instrumented tree and orchard is the first one. This is where we're doing a lot of our orchard imaging work, environmental sensing, and also we're building a Bluetooth mesh network sensor. Our sensor interpretation is the second research aim. In there we do 3D reconstruction, and we look to get the organ metrics out from the imaging data taken in the first research aim, as well as looking at pest and disease machine learning model detection. Physical sensing systems, here we're looking to create a non-contact or proximal NIRS sensor, so it's near-infrared spectroscopy, and wireless photosynthetically active radiation spectrometer that can do multi-band, multispectral band detection. So that's where the light quality measure comes in. And the fourth research aim is one good reason to have a co-lead, and that is that they can have skill sets that you don't. And in this case, I do co-lead this program. This is a little bit more her strength, Carmen Choi. We have a work on DNA sensing here, so CRISPR-Cas technology that we have been using here at Plant and Food to do diagnostics for bullseye rot. And we're also looking at CO2 and volatile organic carbon compound sensing within that program as well. So this is our single tree scanning platform. It's a flexible research device that we've been using to scan a camera across the face of one of these plain accordion trees. They're about 3 meters wide and about 4 meters tall. And we're scanning principally that 31.4 megapixel camera across the face of that tree right through the growing season, more intensely during canopy development. We're using 12-bit imaging. It's quite a graphic example of why that's useful. So high dynamic range imaging is the other term gets used. Most of our cell phones do it out of the box. We don't necessarily understand what it's doing, but this is sort of what would happen if our cell phones didn't have it. We'd see the image on the right. And it's certainly what we see if we don't take advantage of the 12-bit image sensors that come on the cameras we are using. This is one of the 3D reconstructions that's been done from, actually there's two examples here of the 3D reconstruction that's been done from this stationary rig. There's a dense grid of images at 100mm centers. It's about 850 images, and this is using the Gaussian splat technology published, I think, last year, mid last year. So you can see the base point cloud that's generated there. You'll see in a moment a whole lot of cones, which I'm hoping this isn't coming through too stuttered for you all. This is the Gaussian splat rendering that you can see here. It's near photographic quality. And we get these depth fields as well that can be seen. This is the tree with canopy. You can see that we can, stop rendering in the distance and just isolate the tree that way. We hope to use this to build towards getting the full organ level metric out. So that's leaf size, each individual leaf size, even bud fate at the beginning, as well as fruit growth development and other measurements. And many thanks to our collaborators at the University of Canterbury who do these 3D reconstructions for us, particularly Oliver Batchelor. We are then working towards taking these measurements into the field, so away from that one tree into a block level assessment. At the moment, we have a working prototype, as you see there, based on 4 cameras, which will soon be upgraded to 5. We're using a little robotic platform that a New Zealand robotic startup company supplies, and we've developed a passive stabilization system for a 4-meter mast to capture both sides of the canopy as the robot weaves up and down the interrows. So these image sets will be used for both machine learning model training. So there's a pest and disease detection as well as the organ detection, and then move on towards 3D reconstruction in the future. In the third research aim, we were talking about proximal near-infrared spectroscopy. Many of you in the room might be familiar with some of these devices in the top left. They're contact-based, handheld near-infrared spectrometers that can have models made and loaded onto them for dry matter is a reasonably common example. Bricks might be another that you can have loaded on, so you can do non-destructive analyses with these. We both need to and want to and have the skill set, fortunately, to have a go at detaching these devices from the fruit. They have often a rubber shroud around them that's supposed to make good contact and keep the sunlight out, but we have a technique where we think we can ignore the sunlight and use laser sources, modulated laser sources to do spectroscopy at distance. The Bluetooth mesh sensor system, you can see here is a CAD drawing in the top right of that device. It's just fits in a small radiation shield with its battery. It does the photosynthetically active radiation multi-band sensing. You can see the spectral bands in the bottom right-hand corner of the screen. And the idea here is that it also does temperature and relative humidity, but the idea is that we can get a high spatial density measurement of both light quality and those temperature and humidity measurements throughout a canopy of a tree even. The cost of some of this sensing can be very expensive when you need a lot of it, and one of the goals here is to reduce the cost by sinking the cost of development into the program. And in our final research aim, we're looking at doing effectively, point of care diagnostics for horticulture. So as I mentioned earlier, we're using it's an isothermal technology called LAMP, which, very simple terms, if the particular DNA that your test has been set up to detect is present, you will make a fluorescent dye available that you can then shine a blue light on, and you can see in the little diagram to the right, they light up like little fluorescent. The tubes light up as with the fluorescence. It's quite sensitive, the test we have running at the moment. For any of you who understand the technology, that's 13.4 copies of the DNA that it can detect, which is quite low. It's working for bullseye rot, Neophorbrea alba, and our next targets are canker, black spot, and fire blight. And within the volatile sensing part of the program, we have been exploring these non-disperse infrared sensors that you can buy reasonably cheaply. They are effectively an absorbance spectrometer at a single wavelength. Quite useful for measuring environmental CO2. So we're looking at how we can spin them out into the field. You can see one installed in the center of the screen there within a repurposed radiation shield. And for volatile organic compound sensing, we're having a look at these photoionization detectors. They're not specific, but they are very sensitive, and we're hoping to create, if you like, another sense for our mobile imaging rig solution that will be able to pick up plumes of volatiles as it's weaving its way up and down the orchard. And yeah, just so that's me. Just some acknowledgement. Obviously, a large team of researchers at Plant and Food, the great team at UC Vision at the University of Canterbury, and our funding body, the Strategic Science Investment Fund from NBIE. Thank you.